All right, everyone. Oh, here we go. Okay, so yeah, today I'm going to be talking about some new geologic constraints that tell us about the Holocene history of Pine Island Glacier. So I wanted to give a big shout out to all my co-authors, but specifically to who are in the audience today. That's Ryan and Joe, without which this paper wouldn't exist, or this project, and it wouldn't be nearly as good as it is, or at least I think it's pretty good. So I don't have to talk too much to this audience about why we should care about places like Pine Island Glacier, but just to go over it really briefly, so you can see Pine Island in yellow, Thwaites in purple there, and some smaller friends in green. So all of these glaciers drain into the Amazon Sea embayment. They represent about 3% of the Antarctic ice sheet area. But, oh, I've skipped ahead a little bit to this other cool GIF I made. But, yeah, they represent 3% of the area, but 36% of the mass lost from Antarctica has happened in this part of Antarctica since 1979. And as we saw earlier, we're worried about parts of the Antarctic ice sheets like this, where the seabed the bed beneath the ice, gets deeper below sea level the further inland we get. So it's for a long time before I'd been born too, that this has been referred to as the weak underbelly of the West Antarctic ice sheet. So Pine Island in particular, it's the largest Antarctic contributor to global sea level rise at present, and contains enough ice within itself to raise global sea level by about 0.6 meters. So the point of all of this kind of research that I'm going to talk about today is that we give paleo constraints to numerical modelers, and then they can test their models to reduce uncertainty when they simulate the future of these ice sheets. So here we have zoomed in a little bit to the Amazon Sea embayment. So you can see Pine Island there at the top, and then there's Thwaites as well. And you can see that grey line there. Oh, I do have a laser pointer. This is Pine Island Trough, which you've also heard mentioned earlier today. And these black dots here are the locations of a bunch of, or in fact all sediment cores from the Amazon Sea embayment that have yielded radiocarbon ages. So these radiocarbon ages, which you can see on the right here, we've got age and then distance from grounding line. They provide limiting ages on the timing of grounding line retreat from the shelf edge over here, about 20,000 years ago, up to where Pine Island Glacier is now. So you can see as we move from close to the shelf edge, further towards where it is now, we move through time. And you can see we've got this big gap at the end. So the most proximal constraints to the modern grounding line are located around 120 kilometers downstream, at which point we think grounded ice retreated just past this point by about 9,000 to 11,000 years ago. So what we wanted to do is see if we could fill in this gap for this large glacier. Like, what was it up to? We know that it was around here, and we know where it is now, but how did it get from A to B? What kind of rates was it retreating? So to get an insight into the sort of post-11 to 9,000 years ago history, we can turn to another archive, which are terrestrial constraints. So these ages I'm about to show are cosmogenic nuclide exposure ages, and that's what I'm going to be talking about with the new data as well. So these are dated glacial deposits from exposed mountain surfaces. And you can see here, we've got some mountains here in the Hudson Mountains, and they are next to Pine Island Glacier's neighbor, Larter Glacier. And these ages over here, so you'll see another plot of this later, we've got the elevation and then the age down here. And you can see these ages. So these will tell us when Larter Glacier thinned to reveal these mountain surfaces. And you can see most of these ages are around 7,000 years ago. So we know that Larter Glacier here thinned quite quickly around 7,000 years ago by hundreds of meters. And what we were wondering is, can we work out if Pine Island Glacier did the same thing, which is right here. So to do that, we, and by we I mean Joe, went and collected a bunch of samples from all these sites, not just these sites, but even more that aren't even labeled in one field season. And these sites are directly adjacent to Pine Island Glacier. So the glacial deposits from these mountains should tell us information about the past of Pine Island Glacier more directly. So you can see the sites here. So Evans Knoll is the furthest downstream adjacent to the modern ice shelf edge. And then we move upstream from Winky, Nunatak, Shepherd Dome, Inman, Nunatak. And then Mayers, Nunatak is adjacent to the grounding line right at the middle of the sort of fast-flowing trunk of Pine Island Glacier. So you can see a couple of the sites. So they are, I think, pretty gorgeous sites. And the contrast between that dark volcanic bedrock and those lovely granitic glacial erratics is pretty textbook as far as you can get, really, as good as you can get. So not to say that Joe's job of collecting the samples wasn't difficult, but identifying these was, I would say, not too difficult. So you can see that contrast is lovely. So yeah, we present 27 new beryllium 10 ages from 5 nunataks directly adjacent to Pine Island Glacier. So we want to know how thick was Pine Island in the past, and we're interested in if it also thinned rapidly around 7,000 years ago. So here are all the new ages. So you can see the ages, again, are on the x-axis and the elevation is on the y-axis. And the different sites have the different colors there. And we've learned that surfaces up to about almost 800 meters above sea level were covered by ice in the mid-Holocene, or prior to the mid-Holocene, sorry. And then there was rapid thinning of Pine Island Glacier around 7,000 years ago. So if we put the previously published ages on the same plot in gray, you can see that they line up pretty well. So Pine Island did thin rapidly around the same time as Last Glacier. So that's not particularly surprising, because it is directly next to one another. And we've also seen, over the last 10 years or so, loads of sites around Antarctica where people have done the same kind of study have found rapid thinning around 7,000 years ago. So we wondered if we could glean anything else from this data set. So, okay, there's a lot going on here, but we've basically plotted up the sites separately, but geographically. So we move from furthest downstream at Evans Knoll on the left, and then we move from left to right, we move upstream to Mays Nunatak, which is approximately adjacent to the grounding line. And then again, this is just elevation and age. And then all the data are over here, with 2 old ages conveniently cut off of these. So we noticed 2 things when we plotted everything together like this. So the site furthest downstream, this is Evans Knoll, you can see these ages are clustered around 8,000 years ago, rather than being spread out in any manner. So the thing we know about Evans Knoll here is that thinning here, and when you see the rest of the data, it will make sense. It happens earlier than the other sites, at 8,000 years ago, and also fastest. So when we computed median linear thinning rates for the mid-Holocene or early Holocene for these sites, this site yields by far the fastest thinning rate. So when we look at the other sites, you'll see that these ages are a little more spread out from like 8 to 6,000 years ago, rather than just around 8,000 years. So thinning not only happened more slowly at these sites, but also happened a little later, is a little more delayed versus the furthest downstream site. So if we look at everything again together, what we think this means, or what we are inferring, is that the rapid thinning at Evans Knoll furthest downstream is recording the arrival and stabilization of the grounding line of Pine Island Glacier about 8,000 years ago. And then these sites upstream are recording this delayed propagation of this rapid thinning at Evans Knoll up about 50 kilometers of the glacier. So if we place our inferred timing of grounding line retreat on the same plot you saw earlier, so these are all the radiocarbon ages, and here you can see our inferred timing of grounding line retreat to around Evans Knoll. You can see that it does post-date the marine record, so it is consistent with it. So we know it had to pass through or by Evans Knoll at some point in the last around 9,000 to 11,000 years ago. So we think it's happening around 8,000 years ago. So we think we've improved our understanding of the grounding line history, both temporally and spatially, by, from 11,000 years ago, 120 kilometers downstream of the modern grounding line, to 8,000 to 6,000 years ago, about 50 kilometers downstream. And then we wondered what kind of factors might have had a part to play in stabilizing the ground line of Pine Island at around 8,000 years ago. And we noticed that this is coincident with a couple of things. So firstly, the removal of the influence of melting northern hemisphere ice sheets on sea level around that time. And then also we know that sea level was falling in Pine Island Bay by, and then we think likely before 5,500 years ago. So we think these 2 factors may have helped to stabilize the grounding line at this time. So as always, I've whizzed through my talk, so that means there's going to be questions. Well, you don't have to ask anything, but there's time.
Thanks, Keir. We do have time for questions. Yeah.
I should have said this came out 3 weeks ago in geology, which is pretty cool too.
Thank you very much for the talk. I was wondering if your data set is able to make the distinction between a monotonous retreat or if there were some advance and retreat during this period. So is it always in the same direction, or there is going faster and slower during some period and even backwards?
Yeah, I'd say definitely with these terrestrial constraints, we can't tell the difference between them. So we're just assuming that it's moving in one direction. But yeah, without any like subglacial bedrock, we wouldn't be able to tell, I don't think. But yeah, that's a good question.
Nice talk.
Yes.
I'm just wondering, you know, some of the data we have from Eastern Ross Sea suggests that the grounding line can hang out a long time in a position while there's much deflation that was going on. So not necessarily a direct correlation between the deflation in the interior and when the grounding line shifts. Any thoughts about that, what your data might reveal?
Yeah, so it's definitely an assumption we're making when I think it's more the difference between that one site and the rest of them is why we think we may have a bit more evidence for the grounding line to be retreating, because we knew it happened to happen at some point. But yeah, I'm not sure. I guess we won't really know until someone draws a core or finds a grounding zone wedge under there, and I would love to see that, but whether we're right or wrong.
Thanks, Keir. Right, we'll move on to our final speaker of the session. That's Taryn Noble, and we're going to move from West Antarctica into East Antarctica.